So thank you very much for the invitation and for the introduction. Good morning, everybody. So this is joint work with Luc Lehérissi, who is a researcher in Nice, and Sylvain Lecorf, who is professor in Sorbonne University now. And the first part of the talk will be joint works with both of them, and then later with Jérémy Capitao-Miniconi, who is a PhD in Laboratoire de Mathématiques d'Orsay with me. So the general idea is that high-dimensional data have a low intrinsic dimension. So it's a non-subject that you have to learn with. So to make a dimension reduction, either because having too many dimensions makes learning very difficult, or because you want to learn explicitly what is about the support of your data. So there are many methods that have been developed through years. Feature selection, feature projection. You can project on linear spaces using the old method, principal component analysis, or on nonlinear structures using, for instance, kernel principal component analysis. But here I will be interested in exactly understanding the intrinsic support of the data, and in the case you have noisy data and you, the idea is to understand what kind of noise we can deal with. So I will start with ideas about how you learn the intrinsic support of the data when you have no noise. So you have access to points. So these are research that started in the 80s. Of course, learning support is older, but these are the geometrical ideas that came up since the 80s. So you have points on some low-dimensional structures, such as a torus. The first one is a torus and the other one is a sphere. So the first idea, very simple idea, was to put balls around the points, and then you recover the support when you adjust the radius of the sphere as the ball as in a right way. Another idea was to use what's called the tangential Delaunay complex and local principal component analysis. The idea is then when you have the points, oh my God, oh, this is not the right way. It's here, it's here. So with the points you make the Voronoi diagram. Then when the points share the same Voronoi frontier, you put an edge between them, and then you use the tangential space if you know it, and if you don't know it, you estimate it using local PCA. If you have many points, then you can recover the structure. So there are results about such a method, and a more recent one is to use local convex hulls, and then also you can recover the points. And then with all those methods, through the years and very recently, you know how close you can be with endpoints to the structure you want to recover. And then how close you are depends only on the intrinsic dimension, and you know exactly how. And the results depend also if you have a boundary or if you don't have a boundary. Well, these are very technical points I will not talk about. But then what happens now when you have noise on your points? So the ideas, first the ideas were developed using the same geometric ideas. So the first results are when you have small noise. So this is a sample with small noise, you see, it's around the sphere. So you can use the same geometric ideas because tangential Delaunay complex is stable enough, and then the upper bounds between what you reconstruct and the unknown hidden structure depends also on the level of noise. So the fact that it is stable says that the upper bound is smaller than the largeness of the noise, but still you have to have a small noise to recover something very close to what you search. Other results consider clutter noise, that is, you have points on the structure and other points that are uniform or around uniform in some domain. So the problem is to remove the points that are not from the structure. And the idea, again, is geometric. So you can do, for any structure, any possible structure, you put something along the tangential space, and then you count how many points you have there. And for each structure, you count the minimum or around each point of how many come there, and you take the maximum of all possible structures. So this is not a very computable method, but still it works, because you see that if you look around the structure, then you have many more points than everywhere else. And the more recent idea in geometric ideas was to consider, well, I didn't put a figure, but the idea is that if the noise is uniform enough on the neighborhood of the structure, then the structure is in the middle in some sense, and then you can recover it, and you also have upper bounds. So what I will talk about here is a different point of view. It is the modeling stochastic point of view. And then the new result is that if you consider additive noise with very, very weak assumptions, then you can recover the hidden structure with very weak assumptions, and not knowing the distribution of the noise, which can be anything, which can be any large, well, I will explain further. So the stochastic modeling means that data are understood as random variables. The distribution of the points is unknown. I will consider points which are IID, independent, and with the same distribution. And what we have to learn is about the distribution of the points. It's hidden in the unknown distribution. So it can, here I will mostly consider the support, but it can be also the radius if the support is a sphere, or I will have results also on the distribution itself. And we want to use only functions of the data to give results. And of course, the idea is that if you have IID data, then empirical measure concentrates enough and to give meaningful answers. So the evaluation of the estimators is through risk function. That is, you compare your estimator with what you search using some distance, which is a loss function. Then you take the expectation, and you want estimators that minimize the maximum risk over some class of a hidden structure. So I will give upper bounds and lower bounds results on this. So I didn't say, but please feel free to interrupt if something is not clear, or if you have questions during the talk. So the model will be the following. The observations are corrupted versions of a signal X, and the corruption is with additive noise, which is independent of the signal X I'm interested in. So some examples, some figures. Here I will show figures of the hidden structure is a circle. Here it can be a sphere. So this is a small Gaussian noise, a small standard Gaussian noise with the same sigma in all the same variance in all directions. So it's not difficult here to recover the circle. If you take a much larger variance, then the structure is really hidden. So the question is, where is the circle here? Here you have a corruption which has different variance in each dimension. And here the noise is different. It's not Gaussian. It's a combination of a Dirac measure in zero and an exponential which has only positive. So here it looks more difficult to recover the circle. So I will give results that say that even if you don't know that you have a circle hidden there, you can recover it. So first, I'll say some words about what's called the deconvolution problem. In statistics, it's an old problem on which there is a large literature. So the grand idea is that if you take the Fourier transform, that is the characteristic function of the measures, then the characteristic function of the observation is the product of the characteristic function of the signals with the one of the noise. So that in case you know the noise, and all the statistic literature until, well, I will say until the work I will explain later, is about known noise or having data on the noise that allow to estimate this separately. Then if you know the distribution of the noise, then of course it's not difficult to estimate the characteristic function of the signal by dividing something that you can estimate on the data by the one you know. But of course you see that this way, when this becomes very small, then you have a large variance, I will say. So the point of the literature is to choose on where you use this, where you do not use it because it's too small, to smooth everything than to invert. So there is much technical points to do to get good estimators of the distribution of X, but this is the grand idea. So here I will consider also, so the more literature on that problem is in the case where the signal has a density with respect to Lebesgue measure and then estimating this density and recovering things using that. But of course, if you have low dimensional intrinsic support, the signal has no density with respect to Lebesgue measure, and you have to, well, it becomes a bit more difficult. So let me also say a word in the case, so people have been interested also in such the deconvolution model to estimate the support using Gaussian noise. So those two words are about estimation of the intrinsic support of the signal in the deconvolution model. When you know the noise and it is Gaussian and you know the variance of the Gaussian. So in a paper by, there is a paper about low intrinsic dimension in which you get an upper bound in Hausdorff distance of the estimator of the support, which are not far, but you see, first a remark is that in such deconvolution problem, the rate of convergence, especially with Gaussian noise, is a negative power of log n in general. So in those works, you have assumptions, and you need assumptions on the regularity of the support. And there is another paper, more recent, about estimating convex bodies in high, well, there is no dimension reduction here, but it's still a difficult problem. The support is a full dimensional convex body. And then again, the convolution leads to power of log n rates. And here the upper and lower bounds do not match in both papers. So, of course, knowing the distribution of the noise is a strong assumption. And there are earlier works by Alexander Meister to understand if it can be bad to have this assumption. And he proves that when you're interested in estimating the density of a signal that has a density, even in real valued signals, then you can make huge mistakes by assuming something, and when in fact the true distribution is misspecified. So he proposed a method when you only know the characteristic function of the noise on not on the whole space, but still you know it, and then he gave the results. So the question here will be to understand if it's possible to get rid of the knowledge of the noise. So the answer, as I announced, is yes, but of course you need assumptions. So I will explain the assumptions I put on the signal and the noise, which are very weak to my opinion, but to get answers. So there are two questions. First, is the model identifiable? That is, if you have infinitely many data, that is, if you know the distribution of the observations, the full distribution, can you recover what you want to recover? And then, if you now have only finitely many data, are you able to invert the problem? That is the inversion continuous enough so that you can solve the problem with finitely many data? So I will first focus on the first question of identifiability. So let me restate the question. So the question is the distribution of X uniquely determined by the distribution of Y? Or is it possible to get the same distribution for the observation with different observations of the signal and the noise, in which case it would not be identifiable? But the good news is that yes, this is true. You can recover the distribution of the signal hidden in the noisy distribution of the observation with very weak assumptions. So the assumptions are as follows. I will state very precise assumptions just after, but the ideas are that you need more than 2 dimensions, at least 2 dimensions. It's possible to do this with no assumptions on the noise, except that you can split the dimensions in 2 components for which the noise has independent components. The signal has light tails, so of course if you are searching for low-dimensional structure, especially compact structures, that's not a problem. And you need some dependency assumption on the components of the signal. So the difference between noise and signal is that one has independent components and the other non-independent. This is the rough idea. The technical way of saying this is as follows. So you can split your observations in 2 dimensions, one D1 and one D2. The general dimension is capital D. So if you look at the same split for the signal and the noise, for the noise the 2 components are independently distributed. So now I define, to state the assumption about the signal, I define the characteristic function of the signal. And then I assume some boundedness at infinity of this characteristic function. So if I say here, I put I, it means that I have the Laplace transform, and the Laplace transform grows at most as an exponential power of lambda, of the norm of lambda. So in this case, you can develop this in a multivariate analytic function, so you can define it over the whole multidimensional complex plane. So now it is defined in the multidimensional complex plane, since I assume something on the growth of... so I didn't say that assuming such a growth says that the tail is not too heavy to be able to bound this like this. So this what means light tails for the signal. And then the precise assumption is the fact that if you fix one of the two variables, the function, the multivariate analytic function, is not identically zero. It can have zeros, but it cannot be zero everywhere in the other variable. So this is some dependence assumptions, because I will assume that the growth of the signal with the rho in the previous slide, here this rho, I will assume that rho is less than 2. So this excludes Gaussian signals, because for Gaussian distribution, you have this, but with rho equals 2. But the noise can be anything. It's only about the signal. So if you consider independent variables in the components, it cannot satisfy this assumption if they are independent, except if they are Gaussian or deterministic. So it means that if you exclude Gaussian and deterministic, the signal cannot have independent components. So this is why I understand this assumption as some dependence assumption, though it is stated in a more technical way. So the results we got with Luc and Sylvain is that if you put those assumptions and you only have the observation that is the distribution of the observation that is of the noisy corrupted data, then you are able to recover the distribution of the signal and the distribution of the noise. Of course, this is only up to translation, except you assume something about the translation, because of course, if I come back to the model, you of course see that if you translate x with m and epsilon with minus m, you still have the same, and you can not recover that only based on data. So you can recover, based on the distribution of the observations, everything, as soon as you have those very weak assumptions on the fact that the signal does not have heavy tails and has some dependency in the components. So now let's try to see when it holds, in particular for us when we want to recover the support of the distribution of the signal. So some remarks first. So if you add independent variables and they have light tails, then the sum satisfies the dependence assumption only if and only if each of them satisfies the independence assumption. That is, you have to remove the noise satisfying this from the signal. The signal is the signal. Another remark is that if you translate, or if each component you make a linear transformations, it does not change if the dependence assumption is satisfied. So both of these things say that no matter, to understand if the dependence assumptions hold, transforming linearly each component or adding something that satisfies the dependence assumptions does not change. So I did not say about the first point is that this makes the possibility to change dimension. If you are able to prove something for you, then adding a dimension, something different in dimension allows to get the proof for the fact that HD holds for the sum. So this may help for understanding what kind of support you can handle. So another condition which makes more which makes things more easy to understand, is that you satisfy the condition. Well, ADEP is not the good notation, it's HD, it's copy-paste from another paper. Is that in each component RD1 or RD2, you can find a set in the dimension where if you say the component is here and if you make it smaller, then you will strengthen on a point in both directions. So using this condition, you can exhibit sets for which supports for which everything works well. So any closed Euclidean sphere, any ball, any strictly convex set satisfies the assumption. The boundary of any strictly convex compact set, and more generally sets or boundaries of such sets that satisfy what I showed earlier in both directions. I'm interested, I decomposed my signal, that is somewhere where you are strictly convex in both directions. So it's much general, and some almost everywhere in the set of sets results holds also. So it says that almost any, except very specific structures, can be recovered without knowing anything on the noise. So this was the identifiability result. And now let's focus on how it's possible when you want to recover your structure based only on data, that is the estimation question. So I have n observation, IID from my model. So I assume that my signal has a distribution which is unknown, with support we call calligraphic M. So the first step, I will say we have an algorithm, but it's not very easy to handle with. So I will say that the results are mainly theoretical in that sense. But still we have a proposition for an estimator that's nearly optimal. So I didn't say a word about the proof of the identifiability theorem, but it's based on characteristic function and on the property I've shown you about deconvolution, is that characteristic function multiply when you add independent variables. So it's based on such things and complex analysis arguments. And the way it's done, the proof gives a way to build a contrast function, something that allows you to estimate the characteristic function of the signal without knowing, again, the characteristic function of the noise. But you have a criterion to build. So this is the basic step of everything we've done on this subject of deconvolution without knowing the noise. The first step is to get the good estimator of the characteristic function of X. Then, how shall we build an estimator of the support? So, of course, the distribution in general, if the support is not full dimensional, the distribution is singular with respect to Lebesgue. So, you can do, if you smooth the distribution using a kernel in all directions, you can transform it in some density with respect to Lebesgue. If you smooth, you have a density around M, and if you the less you smooth, the more you shrink this approximation of the distribution. So you can estimate something which estimates this smoothed distribution G. How do you do that? So you have to truncate the polynomial expansion of the estimator of the characteristic function, and doing so you do something interesting because you know it is multivariate analytic. So you truncate it, so there is here something that you have to choose, what's the degree of the multidimensional polynomial. You multiply by a kernel that smooths when you invert, which is the smoother of you are interested in. But of course, you have a smoothing parameter, h, that you have to make become small so that you concentrate the more on the distribution. And then you invert your Fourier so that you get something which is some density, which will become close to G if you make all this, if you choose them rightly, so that it means that around the support it will become very large, and far from the support it will become very small. So the idea is to take an upper level set of this thing, and this works. But you have to choose the truncation of the characteristic function, the smoothers of the inversion, and at which level you take the upper level set. So first, before getting the results, the loss function is the Hausdorff distance. Since I will allow signals that have non-compact supports, I'll truncate the Hausdorff distance. So I look at the Hausdorff distance inside some fixed compact set. So I didn't say when I introduced the Levy-Tail assumption, the rho, I said if rho equals 2, it's Gaussian, it's excluded, so it's in between 1 and 2. If rho equals 1, this is exactly compact support, but if it's between 1 and 2, you have non-compact support. Well, that's it. And you look at the Hausdorff distance between what you estimate and the true one inside a compact set. And I will consider distributions for the signal that are AD standard. So this is a standard assumption, always used assumptions in topological data analysis, that is in statistics interested in recovering geometric characteristic of something. And it says that it fixes things that says that your support, I'm interested in that, your support has at most dimension d, little d. Then the results is that the maximum risks over what I'm interested in particular the light assumption and the intrinsic dimensions, etc., says that the Hausdorff distance is upper bounded, so this will be the main term, a power of log n, negative power of log n. So I will point the fact that this depends on rho, which means that though you are inside the compact set, it is deteriorated if you have points if the tail is heavier. So this is larger if rho is larger. So the rate, I mean. The rate deteriorates for signals having distributions with heavier tails. The methodology I didn't say because of course you have to choose all what I said. But you do not need to know the intrinsic dimension. This is different with the works I mentioned earlier, where you had to know to fix all the parameters, you had to know the intrinsic dimension. We do not need to know the intrinsic dimension. It's possible to adapt to unknown rho. And then there is an almost matching lower bound. That is, you can prove a lower bound for this estimation problem, which here is the same except the log-log term on the upper bound, when rho is larger than 1. And when rho equals 1, you lose some small log factor in the lower bound. So they are only almost matching bounds, but still more matching than earlier works that assumed no noise. And the lower bound proof uses the simple 2 points method. So though it's not so simple because you have to choose supports such that the distributions are as far as possible in Hausdorff loss, and add noise such that the distribution of the observations are close enough to have total variations, distance upper bounded. So, well, it's not so easy. So this is the end of what I wanted to explain. So I will just say what you can remind of. First, that you can perform deconvolution for multivariate signals without any knowledge of the noise distribution. That can be any large, anything you want, on the very weak assumption, that is the assumption still that you have independent components. So it means that directions mean something. So, well, depends on communities, but it's a very weak assumption, though it's an assumption. Very simple geometric assumptions allow to apply the theory for the signal. So I gave almost minimax risk in Hausdorff distance. The risk depends on the tail of the signal distribution. And I didn't mention, but in the same setting, we have other results. We can give results about the estimation of the full distribution. Of course, the risk is something that allows to compare singular distributions. So this is for Wasserstein's risk. And if we know, that's an earlier paper, if we know, but still recent, if we know that the structure is a sphere, then it's possible to estimate the radius. So it's a sphere hidden in noise without knowing anything about the noise. You can estimate the radius at almost parametric rate. So that's it. And these are the papers you can look at if you're interested in the subject I've talked about.
Elisabeth, you have question. Yes, I have a question. Your estimator in the end, the upper level set, will have a full dimension, I guess, in general. Even if your support is of much lower dimension. Is there a way to propose a lower dimensional estimator of the support which still has the same rates?
Well, you can plug after that some geometric construction I've talked about earlier, I believe. I didn't think about that, but the ideas of, I believe if you have that, it looks like small noise. Then you have something that looks like small noisy data. So maybe, so there are ways of doing things when you estimate the distribution. Another idea to recover geometric structure is then to sample points from your estimator of the distribution. And then, sampling those points, you can use the geometric constructions with small balls and some things like that. Because you can understand your sampled points as with very small noise, since your distribution concentrates on the true one. This could be something to do.
Okay, and so then it should
but you know, in those works, some of those works assume to know the intrinsic dimension D. Even if it depends on the literature is.
Okay, so maybe it would be possible to estimate the intrinsic dimension with this technique.
Yeah, I didn't say all that, but as soon as we have an estimator that converges in Wasserstein distance, then there is a machinery developed by Fred Chazal and all that, and that allows, as soon as you have that, you sample from this distribution and you can recover many geometric things such as intrinsic dimension, topological structure, etc. So this is some work to do. I don't say it's direct, but there is usual way to do after that.
In your algorithm, you start by estimating the characteristic function of x, and the observation we have are in y. Is it because it's a known technique, or you?
No. It's the main point. I've hidden that, but it's the main new point of what we've done. It's the possibility of estimating consistently this characteristic function, though you don't know the one of the noise. So I didn't show the formula because, well, I thought it was too complicated. But it's something new. It's the very new point in that.
I have a question. So you said that the HG assumption is satisfied. So what were the so is it possible that the component of X are independent, or is it totally excluded? So it's first they must be not independent.
They must. This is how you separate noise and signal roughly. In this, well, it's just the idea, but they have to be non-independent. And you see that if you have supports, except for a square, if you have a cube, they are independent. But if you turn the cube, they are no more independent, for instance. Well, about support, having non-independent components is general.
I was asking myself.
I don't know if I answer your question.
But the components are on two spaces, right?
On two subspaces.
Two subspaces. But it's not a problem if, for example, my signal has two independent components, and my noise two independent components, but in
other directions. No, that can be okay. That can be okay.
But so how?
But you have to. Well, in fact, well, you have to. Well, for the moment, you have to know. No, okay.
Which is the signal and which is the noise?
But you have to know which directions. So you can think that it's a not so weak assumption.
Okay, so you have to know the independent.
You have to know the two spaces.
Okay. I see.
In all what I've done.
So if you know the spaces.
This is in some sense, this is some strong or weak. I don't know. It depends on some strong assumption. That's true. You have to know that.
So you have to know a priori the two directions where the noise are independent, but you don't know the distribution at all.